FDP on fundamentals of smart grid. So we welcome sir uh, for date and delivering the lecture. So we will continue the lecture which was there yesterday. Hybrid AC and DC microgrid. That part will be continued. So please stay tuned. Over to you, sir. Thank you.
A very good evening to all of you. Thank you very much for joining on Saturday. I could see that probably all 30 odd students joined, and I'm very confident in next 5-10 minutes, the rest all also may join. Today we'll be talking about AC-DC hybrid microgrid and their control as well as operations. We have gone through DC microgrid control and operation, AC microgrid. We are interested to understand today what exactly the challenges are and how the control mechanism and operation energy management can take place during AC-DC hybrid microgrid operation. Now, when you talk about AC-DC hybrid microgrid, once again, that AC-DC hybrid microgrid can operate in a grid connected mode as well as it can operate in isolated mode. Okay. So let us focus on grid connected mode of AC-DC hybrid microgrid. In a grid connected mode, the power management strategies can be classified into two types. Means AC-DC microgrid, which has been connected to the main grid, and in which actually power management strategies can be classified into two types. What do you mean by power management strategies? Power management strategies means how the load can be met with help of different renewable energy sources available within the microgrid along with the storage technology with the grid. So when you talk about power management strategy means you have load. That load need to be met by many generating sources within the AC-DC microgrid as well as the storage devices. So that is what we call about power management strategies. And the grid is also there with you. So there are two different mode of operation through which power management strategies are being deployed. One is dispatched power mode. The other one is undispatched output power mode. So dispatched power mode, which is basically the power exchange that takes place between the microgrid and the main grid. Microgrid takes power from the main grid and sometimes it gives back to the main grid. So the power exchange between the microgrid and the main grid is dispatched from a higher level control or optimization scheme. That is basically known as your dispatch power mode. However, in case of undispatched output power mode, the microgrid output power is not at all dispatched. Undispatched means the microgrid is not going to dispatch any power to the main grid at any given point of time. Now, in this mode, DGs and storage energy devices operate on power control mode. The power control mode can now be realized into two different control strategies. One is actually current control, the other is actually voltage control. I request everyone to take the steps, just keep on breaking into different categories, okay? So one is current control mode and the voltage control mode. So in case of the current control mode, which is popularly used in grid connected operations, where the distributed generations output current is controlled, distributed generations output current being controlled in order to track the reference power. Okay, and the output voltage and frequency are determined by because it is grid connected, so grid will decide the power as well as the frequency. Now, when you talk about voltage control mode, similar to current control, where in case of voltage control mode, which can be used in both grid connected and standalone operation, where the DG's output voltage, instead of DG's output current, now it is DG's output voltage is controlled to regulate its output power, and DG behave like a synchronous machine. Why synchronous? Just a minute. When I say it is acting like a, sorry. Yeah, when I talk about DGs behave like a synchronous generator. So synchronous generator means it act like a constant P and constant V. machines. So that is what they are talking about here. Now, in a dispatched output power mode, the microgrid behaves like a controllable source or load to the main grid and can provide a valuable grid support or load management functions as a whole. To realize this, actually, storage energy are considered to be inevitable. Now, to produce the dispatched microgrid output power, power balancing schemes within the microgrid are used to share dispatch power among input power sources. Now, for example, renewable energy sources like distributed energy sources or DGs can work on their maximum power output, that is MPP mode, and other power sources can provide power efficiency between generation and demand considering input power source operation range, response time, etc. Now, moving further, when you talk about undispatched power mode, the grid connected undispatched output power operation mode, all the generated powers are fed to the grid. That means just you generate and push it. There is no control, no strategy. Okay. DGs work on MPPT. You have actually forced your distributed generations to extract the maximum power. And then storage SCs actually are typically charged. Okay. Moreover, ACs can control the smooth distributed generation output power oscillation, especially for DGs with intermittent nature, such as wind and PV systems. Okay. So undispatched is not a very common scenario, but very rarely it happens. Means you have a source, I mean, you are not really bothered, you give everything power to the grid, usko optimization, how to do optimize, how to maximize your output. You are not very bothered about, just control to MPPP and connect to the main grid. Now in grid connected operation mode, that is both dispatched and undispatched power mode, the microgrid means AC/DC microgrid, can be used for the grid support, for example, grid voltage and frequency regulation by controlling active and reactive power delivered to the grid. Now, in case of grid support will be included in the dispatched slash reference microgrid power, in the dispatched power control mode, and in an undispatched power mode, the grid support function will be realized individually through DGs, energy sources, and ILCs. What is ILC? Interlinking converters. Okay. Now we are getting into role of individual device grid connected node, and we are focusing on interlinking converters, ILCs, very important, which is mainly connected in between your DC bus and AC bus, then DGs and ACs. Now, this is a very important concept. All of you please focus on ILC is a very, very important part in hybrid microgrid. So the ILC in an AC-DC coupled microgrid can be bidirectional power mode, okay, DC to AC, AC to DC, DC voltage control mode, or AC voltage control mode. All three options are possible, okay. That you have to decide actually. So let us start with dispatched power mode. With dispatched microgrid output power, two methods can be used for DC link voltage control and dispatch power generation. In the first method, interlinking converter works on DC link voltage regulation mode to set the DC bus voltage on its desired value. Means you have a DC bus, you have a AC bus, ILC is connected in between. So the DC bus voltage need to be maintained. Let's say it's 400 volt. So ILC will make sure that you are able to deliver 400 volts. So the desired voltage is being set. And in this mode, coordination between DGs, energy sources on DC bus, and DGs and energy sources in AC bus is necessary to produce the dispatched output power. Now, in case of a second operation mode, where the distributed generation SCs regulate the DC link voltage on its reference value, while the ILC and the DGSCs on AC bus collectively provide the dispatch power. In this operation mode, ILC work on a power control. Please. Secondary? Not necessarily secondary controllers. No. They're actually not secondary controllers, if you see, because talking about AC/DC microgrid. So they are actually go along with the system altogether. But actually, the role of ILC to me, uh, I can say certainly it is not primary, but not necessarily secondary also. Because you see, secondary control means what? Only when you get a signal of the status, then you react. That is my secondary control. But ILC go along with the DC bus. It go along with the distributed generations. It go along with the energy storage devices. So ILC, DGs, and energy sources, they are actually local. Am I right? Yeah, we can. All right. So DGs in both DC and AC bus work on in undispatched power mode. DGs in both DC and AC buses work on actually MPPT, and the ACs are charged if necessary. They are discharged for smoothing output power injected to the grid, whatever you like to have it. ILC, important now, ILC regulate DC link voltage on its desired value and inject all power generated by DGs ACs to DC bus. Now, if you want to have it 380 volt, that is my desired DC volt, it will make sure that that voltage is actually maintained. Is it okay? Clear. Now, it's very important concept called standalone mode. What do you mean by standalone mode? It's isolated. But we normally, standalone is different than islanded. Please try to understand the similarity and differences. It is not islanded, that's what I wanted to say. So standalone means it has been designed to be standalone itself. Islanded is actually basically due to situation it got disconnected, am I right? So DC bus voltage and AC bus voltage and frequency should be controlled simultaneously. What need to be controlled? DC bus voltage need to be controlled. AC bus voltage need to be controlled, and frequency also need to be controlled. Power balance should happen in both AC and DC bus. Means all the loads and all the generations connected to AC bus, the balance has to happen here, and also in the DC bus, all the generations, all the loads actually must satisfy. Okay. For AC bus voltage and frequency controlled, ILC works on AC link voltage control mode and controls an AC bus voltage and frequency. Let me repeat. In AC bus voltage and frequency control, ILC works on AC link voltage control mode and controls an AC bus voltage and frequency. Yeah. On the other hand, the DC bus voltage can be controlled directly or indirectly. Well, you focus on AC bus, and then DC bus actually you can control either directly or indirectly. So in a direct DC link voltage control, DG's energy sources regulate a DC link voltage on its reference value with either a group control or any mechanism they can use. In an indirect DC link voltage control mode, power balancing between demand and generation will be regulated by the DC link voltage. They will be regulating the DC link voltage. Now, in this operation mode, with the presence of parallel ILCs, it may so happen, instead of having one ILC, you can have multiple ILCs also possible. It is possible.
Shown in figure also.
Yeah. And this is also a PhD topic for your kind information. One single ILC is very easy to control, but you can also have multiple ILCs, and that itself is big problem. It's not an easy joke, okay? So we tried with actually two ILCs, and we experimented a couple of interesting phenomena. Okay, Narendra Babu, PhD of Narendra Babu is parallel multiple ILCs. Okay, in this operation mode, with the presence of parallel ILC, it is possible that some of the converters work on an AC link voltage control mode, and the other control the DC link voltage and balance the generation and demand power. All right. So in a standalone operation mode, coordination among ILC, DGs on an AC bus And DG and energy storage on a DC bus is essential to regulate DC bus voltage, AC bus voltage, as well as frequency, and balance microgrid total generation and demand power at the same time. The power management strategies such as Droop, master slave can be used for AC subsystem, voltage and frequency regulation, and demand power sharing. But for DC substation control, a DC bus voltage can be controlled by DGs and ACs on DC bus directly. For an example, utilizing group control method in DC bus, or indirectly, for example, utilizing power balancing control strategies. It is quite important to note, all of you please take a note also if possible. It is important to note that in a standalone operation mode, ILC play an important role in power management and control. Depends on type of control strategies used in AC and DC buses. This converter can be used on DC bus control mode, AC bus control mode, or output power control mode as discussed. So ILC is quite flexible, it can do at DC side, AC side, in any mode it can operate. However, providing coordination among these control strategies, that is AC bus, DC bus, and ILC, because that itself is another bus actually, is the most important objective in this operation mode. For example, in the condition that DC bus voltage is controlled by DGs and ACs connected to the DC bus, you have a DC bus, so you have many DGs and many storage devices. They decide the bus voltage here, am I right? To DC bus. And AC bus voltage is controlled by DGs and ACs connected to AC bus. The ILC is responsible to manage the power flow between AC and DC. So that means the voltage you fixed here by DC, by AC, so the power flow between AC bus to DC bus will be decided by the ILC. Now we'll see the different power management strategies. So when you have AC-DC hybrid microgrid, we have actually two major categories. One is grid connected and the other one is going to be a standalone category. Just a minute. Okay, so AC-DC hybrid microgrid. So one is actually grid connected, the other is going to be standalone. And the grid connected system is divided into two types. One is dispatched power output, and the other one is actually undispatched power output. Similarly, the standalone is of DC bus control, DC bus voltage control mechanism, or DC bus voltage control mechanism. Now here, almost actually there is a small mechanism I could see. Uh, in the both the types actually, standalone actually, because uh, in the first case, all of you let us come from the standalone side. DC bus voltage control method, we say DGs and ACs on DC bus, DC link voltage control directly, example drip methods or indirectly power balancing, we have already discussed. And the right side, there is a small error actually, we need to make it AC bus voltage control, okay? Just a okay. So DC bus voltage control, and the right one, all of you please take a note, there is a typo. It is not DC, but it is AC. Now, similarly, in case of grid connected, we have dispatched power output method as well as undispatched power output method actually. So whatever we have learned or discussed being summarized in one PPT, right? So power management strategies during transient and different loading conditions, power management during switching of transient operating modes. The first one is grid connected, standalone operation. Grid connected to standalone operation. There are mainly two groups of control strategies for microgrid transition from grid connected operation to standalone operation. Now, when you say actually grid connected to standalone means it is simply dispatched, disconnected due to a specific reason. Okay, maybe shortage of power, probably voltage mismatch, probably could be the way frequency is being generated in the grid, which is not acceptable to the main grid. So I say you get lost, it is connected. So switch of control strategies from current, power control mode in grid connected operation to voltage control mode in standalone operation. And then second will be uniform control in both grid connected mode and standalone mode. Now, different control strategies are used in grid connected and standalone operation mode, and the control strategy is switched between these two controllers. Now, DGs are working on current control modes in grid connected operation mode and switch to voltage control mode to ensure continuous supply of power. Means operating in current control mode, switching to the voltage control mode to make sure the desired power is being provided. To sensitive loads and sharing load demand among voltage control distributed generators. So whatever the load we have, they shared among themselves. This switching of control can be applied to DC-DC converter, DC-AC converter, as well as interfacing or interlinking converters. For a seamless transition, there are a number of recently proposed methods that you can refer to the literatures where the line current of distributed generators can be reduced to zero before switching to a standalone mode or islanded mode, voltage control mode. It is also possible for faster transition without reducing the DG line current to zero. Is it okay? Now, switch of control strategies to realize this control scheme. Switch an islanding detection algorithm, which could be either passive or active, and communication band detection scheme is usually used to determine the disconnecting time instant, which is used to switch the microgrid controller from grid connected to standard. Okay, so you have to identify, and based on that, you can take a action. So this could be either passive, could be active, or could be any type. After isolation, the voltage controller is immediately applied. And synchronization unit works on as an oscillator at a fixed frequency. In case of multiple DGs, if you have n number of DGs, then you have to apply for group control, DG1, DG2, DG3, okay, or other standalone operation control strategy can be applied. Moving to uniform control. What do you mean by uniform control? In the second group, the power management and control strategies are the same in both grid connected and standalone operation mode, and it is not necessary to modify the control strategy during the transition. Therefore, it is challenging to design and implement a robust control strategy to work on grid connected standalone methods. Islanding detection algorithm is not necessary in theory, but it is usually needed due to utility requirement as well as for better control performances. This group may include smaller distributed generations, units that will work in MPPT or current control mode in both grid connected as well as standalone operations. For larger DG group, for larger DG group and energy storage unit, which are dominant microgrid power sources, with some modification, voltage control mode is implemented in different operation mode to avoid control scheme transient. For an example, conventional group method have been modified in using the concept of virtual impedance and combining PI controller with group control to be used in both grid connected and standalone operation mode in the presence of distributed generations. As another example, conventional hierarchical control, if you recall my previous to previous talk, have been modified in order to improve weak disturbance rejection performance of conventional voltage and power sharing controllers to be used in both operation modes of the microgrid. Now, when you talk about how the power is being shared among DGs during transient, become an interesting phenomenon. Okay, so suddenly switch disconnected and immediately you want power to be shared. So it should share the power demand among DGs to continue supply power to the loads within the microgrid. Transient power sharing among DGs or energy storage units are important for both groups of control strategies. And during standalone operation, the Powertronic interface DGs initially picks up the majority of any load step, whatever the changes, they will take it. In some cases, poor transient load sharing exists in the presence of DGs and conventional synchronous generators. In order to improve the generators is necessary. For example, control strategy has been modified for the droop control in order to improve the transient load sharing by changing the droop slope during transient and restoring it to normal in steady state. So what we do in the steady state, we have this characteristic like this. During transient, it can go there, again it can come back, all right? So this is the steady state, but during transient, I want this fellow has to contribute more sharing. So this slope actually I can adjust actually. The synchronous and synchro converter, you know, and the synchronous converters are other methods that allow the power electronic interface DGs to follow the conventional synchronous generator principle and may help the transient load sharing appropriately. Now, previously we have seen that, grid connected to standalone. Now, standalone to grid connected. I like to share actually what actually motivated me to teach all these things in this class today. Because this is a kind of a research problem, okay? So I told you a story that regarding the blackout in this country. I told you, okay? So what has happened actually? So when I talk to my family members, it has been found there is no power and there is no electricity available in the home, even having a distributed generation of capacity close to 1.75 to 1.8 megawatt. Is it okay? So now the worrying part is that why this is not happening? Because when that is not there, the DGs also stops generating power because they don't see any reference here. A little bit of diesel generators they could contribute. Now they're also off. So all the PVs actually, gone to sleep because they cannot generate any power. Now imagine, so what would be the case? So would be the case when it is grid integrated system, when there is a fault, major fault in the main grid, is the microgrids must operate. Microgrid means the campuses are also like a microgrid. MNIT Jaipur is a big microgrid. So from the main Rajasthan grid, actually, this should be disconnected. And whatever the little power we have, that must be balanced in AC. This is my AC microgrid. So within this AC microgrid now, I have diesel generators, I have PVs, I have reasonable loads. So I can see to that actually how the balance can happen. But once my job is done, now the grid has restored. We do not have capabilities to connect automatically.
Grid has to send a signal.
A lot of work need to be done. Once they are disconnected, again connection become an issue. So today we do not have a mechanism like you have a shop, you have a diesel generator. I can put a automated switch based on which actually whenever there is power cut, my DG comes in. Whenever the power is available, the DG actually disconnect. So we have that mechanism. The same mechanism actually if we can have it in our AC/DC microgrid integrated systems, so it can get isolated from the main grid and get connected to the main grid depending upon the situation. It is my choice as and when required. Today that scheme is actually not available in most of the cases. So it is directly connected. It's a single system. If one fails, everyone go to sleep and we say, well, if it would have been the thing, then my system must have been immediately disconnected from the main grid and looked upon the DG as my main grid and my PV started generating. The PV is ready to generate, but the mechanism, the disconnection and the control mechanism is not in place. And the moment the grid is there, I will tell my diesel generator to switch it off and I will see my main grid is a reference. And I will start again generating. So PV generation is not going to stop. Either you are islanded or you are grid connected. Only it will find a, kind of a matching scenario or a reference point with either the grid is my reference or my DG is my reference or a battery is my reference. So this is what actually now the second step from grid to standalone. Now actually we have to go from standalone to grid. So now job is done. You are happy that the grid is in order. Now the standalone system is interested to get connected. Okay. So in the transition from standalone to the grid connected operation mode, which is currently not in practice, and hence during blackout, actually thousands of gigawatt of energy from the PV could not cater the consumers in this country. So that is where actually in the transition mode from actually standalone to grid connected operation mode, other than the control scheme, switch from voltage control to current or power control or through the uniform control scheme, an important task is that the microgrid voltage should be synchronized with the grid voltage before reconnection. Okay, both the terminal voltage should be synchronized. Then only I can clock them. So for synchronization of the microgrid to the main grid, there are mainly two types. One, we have to do that synchronization. Okay. So if you come to Admire Lab, actually we'll teach you how we are doing the synchronization. And we do a physical synchronization. I still remember actually. We are doing a physical synchronization. But there actually we observe, keep on looking at the frequency and then, we switch it on manually. But it's not a automatic system. But the philosophy is actually you can have synchronization through a passive synchronization mechanism or we can have a active synchronization mechanism. So let us understand what is passive synchronization. For passive synchronization, the microgrid voltage and main grid voltage are monitored and the two grids are connected when they have the same phase angle. Okay. So you can keep on measuring the phase angle. When they are actually of the same phase angle, you can plug them. This method is based on assumption that the microgrid and the main grid have very close voltage magnitude. Magnitude is same and slightly different frequencies, which is typically the case. Okay. The passive synchronization is the easiest and probably the most practical method so far. That's what actually we do in the lab also. However, this method will lead to some transient upon reconnection. That will certainly happen. We will explain that transient. However, this method will lead to some transient upon reconnection of the two grids due to not exactly matched voltage magnitude. So you just look closely, okay, 230, 230, 220, 20, then you immediately do it. But still you will experience some transient. It does not guarantee a fast and controllable synchronization process. Okay. The next is going to be active synchronization. Active synchronization can achieve fast synchronization and seamless connection of the microgrid and the main grid and has attracted considerable research effort. Active synchronization can achieve fast synchronization and seamless connection of the microgrid and the main grid and has attracted consideration research effort. So this is also another interesting topic about active synchronization. Okay. However, since the microgrid consists of different type of DGs, severely, severely charging electrical loads, changing electrical loads and storage devices, the synchronization of a microgrid is quite different in comparison to a single traditional machine. So doing synchronization with one machine is easy, but when you have hundred of machine operating in different condition and changing load atmosphere, it is quite challenging. So for active synchronization, coordination of multiple DGs and energy storages is required. We need to have a serious coordination among the machines and storage devices. In some cases, synchronization unit is embedded in the control strategy itself, while in other separate synchronization unit provides the synchronization signal in order to provide microgrid reconnection to the grid. All right, so this is a $1 million solution. If you can have a control mechanism with synchronization, and then you can have a kind of a strategy which can do automatically, inactively. So that's some question. Yeah, go ahead.
So, setting the output of a converter to the equal to the difference with DC.
No, try to understand. I have a main grid with me. I have a hybrid microgrid. We are talking about hybrid microgrid here. Okay. You can think of AC microgrid also, but we are talking about AC-DC microgrid. Now my question is, so you have that PLC, no? PLC of the AC grid, and then here actually you have the point of common coupling. Okay, that is where actually the AC-DC microgrid and the grid is connected. Now my target is, now this is disconnected. There is a switch, you disconnect it. Now I like to connect it. So what time I connect? Only when I experience at the PCC, point of common coupling, actually the voltage will be equal to my bus voltage at this point. Am I right? So who will understand, who will measure, and who will do that job? So that's what passive means. Actually, most of the time, actually, we do it manually, partly we do it, okay? Assuming both the voltages are same, 230 volt, 230 volt, 400 volt, 400 volt. Only the phasors are considered to be slightly different, or the frequency is different. So once the frequency is matched, we click on. But in case of active synchronization, we want it to happen automatically. Means it is there, the system is there, it disconnected, the switch will be automatically closed when the both frequency and voltage are matched. And this is very interesting challenge actually. Yeah.
Can setting another part of the grid as and AC microgrid.
The moment you say grid voltage is constant. There is not portion of a grid. So grid, if it is 11 kV grid, it will experience 11 kV voltage all the time. Am I right? It is expected to be at least. Now you have a microgrid. Let's say you connected a microgrid at 11 kV. Am I right? So it is when you disconnect it, you will not be experiencing 11 kV. Maybe 10.5, 10.7. So when you go back to the grid, you have to make sure that 11 kV is available to you within the microgrid itself. That is important. You have to go to that point and then switch it on. Is it okay? Good, good. So depending on utilized control strategy, the active synchronization strategies can be classified into two types. One, I mean, these controllers are today available in market, but you'll be surprised the cost. The cost is as high as crores, isn't it? So, because very few people have it and they charge like heavily. Am I right? So one or more DGs initiate the synchronization process and the other DGs actually follow them. This is one way of doing it. Second, all DGs take part in the synchronization process simultaneously. Whenever there is a kind of when you start a distribute DG, have you seen a DG getting started? Not normal generator, I'm talking about a big microgrid like. You will see to that actually when there is power cut and the DC is coming to action. All right. We have to see to that actually what it happens initially. You will see a very interesting noise initially and then it will stabilize. And that initial phase is nothing but the synchronization. Okay. So the yeah. So this is very important now. The first group of synchronization strategies mainly used in the microgrid that some DGs are working on a current control mode. The second group of synchronization mode. After synchronization, the microgrid will be reconnected to the grid at the voltage 0 pressing. Okay, so this is very important. And in both type of synchronization strategies, communication system is essential in order to communicate the system information among power sources. Because in the laboratory, we do simply one source and we experiment. But in a real, like a campus, having hundred of generators, hundred of loads, it's very challenging. So power management strategies under different loading conditions, that is in hybrid microgrid, the loads and or the grid conditions can have significant impact on the performance of microgrid. As a result, robust current or voltage control is needed in these conditions. In the presence of nonlinear / unbalanced load, that's what I told you about PCC, point of common coupling. Various control strategies have been used. On the other hand, constant power load, that is CPL, cause instability problem in the microgrid because of the negative impedance characteristic. All right, power management strategies under different loading conditions. The previous one we talked about actually, sorry. Yeah. Good. So this problem is using small signal method and large signal methods. All right. And various solutions have been proposed to ensure the system stability. This includes oscillation compensation technique used to increase stability margin, active damping techniques to overcome the negative impedance instability problem, nonlinear control of AC/DC converters. In addition, in some cases, CPLs are controlled to provide ancillary services to microgrids, such as harmonic minimization caused by Poultronic nonlinear load, shunt active filter, etc. In addition to CPLs, which affect the microgrid stability, frequency, and voltage, dependent loads can influence the microgrid stability very seriously. It has been shown that in a standalone operation, the frequency and voltage deviation are dependent on each other. V and F are linked. Therefore, microgrid may reach unstable operating state as a consequence of loads, voltage, and frequency dependence. For example, induction motors are frequency and voltage dependent loads in the microgrid, where conventional PQ control strategies cannot guarantee the microgrid stability in this issue. Very important. In the presence of frequency and voltage dependent loads, accurate load models are essential for control system design in order to enhance the stability as well as the transient performance. If you look into the future research areas of hybrid microgrid, what do I see? Mainly, they are actually power management, power quality issues. These are all research problems. Parallel operation of ILC, already mentioned, but we have done it a little bit, but still there is huge scope. New semiconductor technology we have mentioned in 2015 itself. This is also a new area, and today, 2025, we are talking about semiconductor, means, yeah, so power conducting devices should be indigenous. Economic concerns, that's very important, because when you talk about load sharing, who has to share what? Transient power management is an interesting problem. Communication system is also equal. So these are the 7 research problems one can work on in the field of hybrid microgrid control strategies. With this, actually, we are coming to an end of this topic, and there are n number of references. Please go through, because this is the longest reference I could see. And for example, reference number 11, a control strategy for flexible microgrid based on parallel line interactive UPS system. So quite interesting articles. Each and every article they have been very genuinely chosen. They're not like random references. So please concentrate. And probably all the literatures that you have discussed of 100 pages, they're taken from those 16 references. But nevertheless, we are slowly switching to another topic, that is PMUs. Why PMUs are important in microgrid become an important question. PMUs are certainly important because the distribution system, because phasor measurement unit is very, very important. And the health of the distribution system can be monitored, and appropriate actions can be taken with help of PMUs, because we cannot do everything manually. Okay, so we need a device uh, which can help me to get the health of the whole distribution system, signal exchanging, okay, stamping of each and every voltage signal at a distribution level is possible through the PMU. But in this unit, we are talking about the optimal placement of PMU, because the cost of PMU is actually very, very huge. If I have a distribution system of 1,000 buses, I cannot afford to place 1,000 PMUs because of its cost consequences. So we need to identify what are those points where the minimum PMUs can be placed. Okay, so we are talking about a little bit of mathematics here, phasor measurement unit placement technique. So we need to do a bit of optimization, dear students. So suddenly we'll come from actually theory control to few equations. Okay, so what we'll be talking about here is introduction, purpose of optimal PMU placement, optimal PMU placement models, problem formulation and experimental results, classical and meta-heuristic optimization technique, and then you will see its application to different IEEE systems. So large-scale renewable integrated power system, which really increases the uncertainty at both the generation as well as demand. So there is a severe mismatch that happen between these two. Advanced monitoring and controlling methods are needed. Real-time information from measurement devices connected in the network is required for the state estimation and other analysis. Today, you will be very surprised to know, for a distribution system, you can determine the losses using data-driven techniques, even for different load conditions. Because when the load condition changes, your flow of the power flow in the line changes, okay? The losses changes. So that means every 5 minutes, 1 minute, every second, the losses changes. So how do I determine? So we know how to determine the losses of a steady state system or a frozen system or a pseudo system. But for a real system, no one can measure the losses. Now there are data-driven techniques which has been evolved, which can easily measure the losses of the distribution system. We'll be happy to know even the topology estimation, So even there is a line came out of the system. So the voltage can be estimated. So you need not work out load flow analysis again and again. So I think there is a tool which can easily tell you what is the voltage change because of certain topological changes. So advanced monitoring and control methods are needed because of the complications associated with the microgrid. So real-time information from measurement devices connected in the network is required for state estimation and for other analysis. Most popular measuring device is here. So it is basically a system measurement device. So then why actually optimal placement? PMU installation is limited by economic and infrastructure constraints. Critical buses, generator buses, tie line buses are prioritized for the close monitoring. PMUs are costly. Optimal bus locations are need to be found to reduce overall PMU installation cost. All right, so optimal PMU placement model. So what we do, network data, we get it, and then we run the base case DCOPF, distribution optimization, and then we go for actually true results. And then we get into PMU cost minimization, state estimation constraints, observability constraints, compare with the true results, and then finally you can get a solution for optimal placement of PMUs. So this is my operating cost minimization of linearized optimal power flow with different network constraints. And you are going to minimize the cost of different generating units with network constraints for power balance, line flow limit, and power generation constraints. So once this is being done, then we move to objective function of PMU installation. So where we say the minimize the summation of PMU's cost. Okay. So I can put everywhere. That is one way. But what are those points I have to choose so that all the data can be tracked? So then you have to get into the state estimation constraints and observability constraints. This is some of the test case systems. We have taken IEEE 14 bus system, IEEE 30 bus system, and you could see that there are 4 dots, blue dots you can see. Bus number 2679 identified to be the best optimal location of PMUs. This is a very, very interesting problem. Okay. And similarly, in case of 30 bus system, bus number 2, 4, 6, 10, 11, 12, 18, 23, 26, 29 are found to be optimal. And then instead of putting 30 PMUs, we can say I can put actually 10 PMUs, or instead of putting 14 PMUs, I can say I will be interested to put 4 PMUs. So these are the experimental results. What is experimental result? Between DCOPF results and the state estimation measurement for the bus voltage angle and line. So you calculate through algorithms the voltage and angles at each and every bus, and through PMUs you determine the values of voltage and angles of each and every bus, and then you compare, and almost actually they are extremely close to each other. So there are many classical optimization techniques. Binary linear programming used to solve systems of linear equalities or inequalities in binary unknowns like zeros and one. PMU is there, it is one, not there, it is zero. Mixed integer linear programming with zeros and ones as variables, at least one decision is not an integer. Nonlinear programming, either the objective function is nonlinear or one or more constraints are nonlinear. Graph theory based study of relationship in terms of nodes and vehicles, vertices, and is used to model pairwise relations between objects. We have a meta-heuristic technique. I'm not wasting a lot of time here because you all know it. You can use one of the methods to get your solutions. There are a lot of merits and demerits of different meta-heuristic techniques, and minimum number of PMUs you can calculate for 14 bus system is 3, for 30 is 7, and you can slowly see like for 57 bus it is going to be 11. So the minimum number of placed PMUs in IEEE transmission test system is used as a basis for algorithm comparison of your meta-heuristic techniques. Oh, okay. And this is a wonderful study for different methods. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 methods, including classical techniques, generalized integer linear programming. You can see the answers are coming to be more or less perfect. Okay. So there was a time we used to ignore meta-heuristic techniques, but now considering the impact of AI and ML in the world today, perhaps they also have some space. So it cannot be ignored anymore. Okay. Because the way everything is working. Okay. So it's very interesting, we all were working on AI and ML before 20 years, but it's not found to be very attractive because there is nothing happening in reality, it's just work on a black box. So we moved to hardware and then we realized, oh no, AI ML is again picking up. So that is what has happened. The world is oscillating. So these are two interesting reference, and you can read it with this note. I think, thank you very much. Wonderful. So, Saturday, I do not want to drag you more. Please have a nice weekend and take care. Bye bye. आज disturb मत करो बच्चे को छोड़ो. No.
Okay, so we end today's lecture over here. So thank you so much, sir. So if you have any query, we will take up it on Monday. You can note it down and we'll say this. Thank you. We'll update the slides on Canvas so you can access it through that link. Thank you so much.
Thank you, Chandrasekhar. Thank you, Rajendra. Thank you, Devchandra Singh.
बड़ा कर दो. ठीक.
ठीक दिखाई दे रहा. Good. Okay. I think I was a bit, kind of